So you know the codes to get in the doors, right? Yep. And so, okay. Anybody have any questions? I'll wait a few minutes, let other people get here, assuming. Hi. So how many of you are mechanical engineers? Okay. How many are you materials engineers? How many of you are neither? Okay. We don't have any nukes this year. Okay, fine. At least not yet. So this is actually the first time I've ever, it was just last spring that I got this registered as a undergraduate course as well as a graduate course. And so this is the largest number of students I've had in a number of years. I used to have this number of graduate students back when I was doing the manufacturing program, which is now mostly at the Sloan School. But I will have to adjust a few things, but I'm not going to adjust too much, okay? I used to teach undergraduates all the time. How many of the graduate students were MIT or how many of the graduate students were not MIT undergraduates? Okay, fine. So we got a number of people who were not MIT undergraduates. I was an MIT undergraduate. In fact, I've been here 44 of the last 46 years. So I'm older than some of your parents probably, or I've been here longer. I know I'm older than some of your parents, but I've probably been here longer than some of your parents have been born. In any case, I am an MIT product and I have some strong opinions about MIT. I have my opinions about teaching, and it's not just at MIT, it's just the way we teach in general in this country. We teach students to take tests, okay? That's what your goal is, doing tests. And the problem is, you're MIT students. You wouldn't be here if you weren't very good at taking tests. So unfortunately, there's no tests in this class, okay? So everything you've learned about classes, forget, okay? I hated taking tests. I used to look at undergraduate courses and determine which ones I would take to see if they didn't have a 3-hour final. I just couldn't stand 3-hour finals. But in any case, what happened to me was in my junior year, which was 44 years ago, I was taking Introduction to Quantum Mechanics in the physics department, and I was doing terrible. I mean, I was getting 15 out of 100s on the homeworks, where average was say 85 in the class. And anyway, then I just figured it was actually an elective for me. I was in course 3. I didn't have to take quantum mechanics. But anyway, I took it, and I wasn't doing very well. And the night before the final, well, I should tell you a little bit more. I came from a southern high school where they didn't even know how to spell MIT, okay? And we didn't send anybody to the Ivy League schools or places like that. It was in Virginia Beach, Virginia, and to them, making it into the University of Virginia was a big deal, right? And they didn't know about Princeton or Harvard or Stanford or anything like that. Anyway, I found out when I first came to MIT, I was in the bottom third of my entering class. I may have told some of this to some of the internship students, so I apologize. But anyway, I came to MIT, found out in the first week I was in the bottom third of my entering class. And they had actually put us in Kresge Auditorium, said, look to your right, look to your left. A year from now, they said, we used to say, look to your right, look to your left. A year from now, one of the three of you won't be here. Isn't that a great way to introduce you to MIT? And they said, we don't say that anymore. And then they put up the SAT scores, and I realized I was in the bottom third of my class. Okay, I was smart enough, good enough in math, I could figure out from the statistics that I was not near the top of my class. And there's a serious problem that you have at MIT as a undergraduate is 45% of you were valedictorians in your high school. I wasn't even the valedictorian. I was number 8 out of 200 in my high school. Anyway, you're very good at taking tests, and you're used to comparing yourself with others. You were in high school, you were used to comparing yourself with others on academics because you would stand out, right? And you come to MIT, and on average, you find you're average, okay? And it's sort of a shock. So I went through that, and so by junior year, I was sort of muddling along, and I'd done okay. It was the first year of freshman pass-fail, so I got passes freshman year. So I take this quantum mechanics course, I'm doing terrible in it. And so the night before, I decided, night before the 3-hour final, I decided I'll just take the textbook and study the highlights, okay? And this was a transformation for me, okay, in my undergraduate and graduate career. And actually, to a certain extent, the way I learned to study and learn on my own. I went into that final, 3-hour final, finished it in an hour and 20 minutes, checked it over. They wouldn't let us leave until you'd stay there at least 2 hours. It's another story. But anyway, so I kind of sat there and checked it over. Got an A in the course. I probably got close to 100 on that final. And all of a sudden, I realized all this fluff they teach you, it's all fluff. Typically in a lecture, there's 1 or 2 themes, maybe 3, that a professor can get across in an hour, okay? And beyond that, you know, all this other stuff is just, it's part of the fire hose, right? And you don't have to learn it, particularly if you're just trying to take a quiz. So from then on out, I quit taking notes in class. So I see you all set ready to take notes. You don't have to take any notes. There's not going to be any quizzes. And I just, for the rest of my undergraduate and graduate days at MIT, I never took notes. I quit studying. It was just like high school and elementary school where I never took books home and stuff. Yeah, I did my homework and stuff. But I used to try to sit there and listen to the professor and figure out what his 2 or 3 themes were. I used to call it guess my outline, okay? Because most people actually do have some idea of what they're going to talk about. The faculty aren't that bad. And so I would try to figure, what are the 2 or 3 themes in the lecture? So that's how I finished up, and I actually, at that point, I did pretty well with grades, because it was a big transformation to realize that most of this other stuff was fluff. So then I became a faculty member, and in the early 80s, I was teaching all undergraduates, sophomores in thermo and stuff. And that's when I really started to learn, well, the students are just, they don't really care that much about learning the material. They just want to pass the quiz. Okay, I don't want to tell you all the stories about how I learned that. But I thought, this is terrible, okay? They should be interested in learning things. And then I realized it's partly because of the way we structure the courses. I mean, you know, you got to pass the quiz and you're competitive with everybody else and everything. So, and I continued to teach along that line through the 1980s, the traditional way. But I wasn't very happy about it. So in the 90s, I kind of became an administrator and the department head and things like that. And I still taught, but as department head, I still taught because I enjoyed teaching, but I was the only department head in the School of Engineering who actually taught a course. Most department heads say, oh, I don't have to teach anymore. And I used to think, well, why are you here on the faculty if you don't want to teach? Okay? But anyway, a lot of faculty have that opinion that they're just bothered by having to teach. And part of it is because they're doing it in the drudgery way of, well, I got to prepare the students to take the quiz, okay? So when I stepped down as department head 14 years ago, I decided, okay, I'm now free. I don't have to do administrative work. I don't have to do anything that I don't want to do for the rest of my career. I can do what I want to do. So I started teaching this course for fun, okay? And then Professor Shu came to me 4 or 5 years ago, and it had been a welding course, and he says, well, Tom, we want you to talk about something broader than that. I said, fine. Okay, so what we did, here's a syllabus of what we're going to teach this semester. There's no quizzes. If you're going to have to make a presentation, and I haven't had this many students since I started doing it this way. You're going to have to make a presentation. It'll be about a 10-minute presentation. We'll do 3 of them a day in an hour, and we'll have some questions and stuff. I learn a lot from the presentations. The students say they learn a lot from the presentations. What's the presentation going to be on? Anything you want, okay? I've had students talk about ornamental doorknobs. They just had an interest in ornamental doorknobs, okay? And they talked about how they were made, because that's sort of what this course is supposed to be. It's supposed to be a structural materials course, and the syllabus for this semester is I'm going to be teaching a series of lectures, typically about 12 hours, on material selection. Dr. Simone Belmar is going to give 2 6-unit modules. One of them is going to basically be I was talking to them yesterday, it's going to be corrosion mostly. And this one is an overview of casting and solidification and deformation processing. So that's going to be 24 lectures. The other 12 lectures, because this is a 12-unit course, right? You're supposed to have about 36 lectures. You need to take one of the other modules. We're videotaping the class. And the reason we're videotaping the class is because some of you can't make it to class every day. I was actually the first person in the early 1990s to videotape a lecture and give credit, MIT credit at a distance. General Motors wanted to take my welding course, okay, at their tech center. And so they paid a lot of money, and MIT agreed to take all the tuition from those 20 students at General Motors and give it to me as a budget to have the advanced visual studies folks videotape my class. And I'd get in at 5 a.m. and we'd, videotape my, to prepare for it, and we'd videotape my class. And I spent a lot of time and a lot of money videotaping the class. And I learned it was actually good for the students on campus too. Because if you had to miss a lecture, you could watch the movie, right? So I determined it was a good thing to videotape, but I didn't have $20,000 or $30,000 every semester to do this. So I decided that I would hire a student, and I've been doing that ever since. And so for $1,000 or $1,500 or something, I can find a student who's willing to make some money. We videotape the class. I used to put it in, starting around 14 years ago, one of my graduate students says, oh, you ought to put it on the internet. So I had a website, and this is from my eager.mit.edu website. And if you go to classes, up there should be a link. I got to check with Dr. Jenkins, who started all this 14 years ago when he was one of my graduate students. You should be able to get a list of the lectures from prior years, okay? So I lectured in the summer of 2013 fusion welding. I did codes and standards in the fall of 2012. Dr. Belmar did structural life assessment. It has become an introduction to structural materials. There's not a lot of us left at MIT. Most people are in biomaterials or photonic materials or electronic materials or, things like that, nanotechnology and stuff. Well, I started out as a welding engineer when I went to industry. They said, you're a welding engineer. So I actually worry about structural materials. You're going to need to pick one of these modules from the past, and you're going to have to watch it on your own, okay? And then you're going to have to basically decide what you want to do your presentation on. We're going to meet every day of the week that I'm here or Dr. Belmar's here. He and I were both down in Texas yesterday and Wednesday, so Mike Baumforth gave you an introduction because it was the first day of class. We didn't want to have an empty classroom for you. So today's my first lecture to talk about the course. I'm supposed to tell you by MIT regulations about certain types of requirements of the course. Here's my notes. So you have to do a presentation. If we meet every day of the week, so officially it's Monday, Tuesday, Wednesday, Thursday, Friday, and Tuesdays and Thursdays are recitations. I have to tell the rest of the registrar that, because otherwise he won't let me have a classroom every day of the week. But we're going to finish up by mid-October, certainly by before Halloween. Okay, I've never gone past Halloween. I don't want to go past then, because as soon as it gets to be, you go off daylight savings times, it's very hard for the students to get here even at 9 o'clock. Okay, I've learned that. In any case, he or I will be lecturing these. I will be here on Monday. He will be here on the 9th and 10th. I've got to go down to Virginia. The 11th and 12th I'll be lecturing. So I know it's going to be a week ahead. You just have to come to class. You can take notes if you want, but why do you need to take notes? There's no quizzes. You can just sit back and relax, right? I'm going to hand out things you can read, and if you want, you can read them. You're supposed to watch these other 12 modules, or 12 lectures of your choice. If you're interested in casting, I did a whole 12 modules on casting. Dr. Belmar will do 2 lectures on casting. I spent a whole 12 modules on casting. I did deformation processing. He'll do something, but I did 12 lectures on deformation processing, if you really want to go into it in some depth. That was when this was all a graduate course. Now I'm kind of turning it, since more of the students are undergraduates, I'm modifying the course a little bit. So I do teach it a little bit differently, but it doesn't really matter. Graduate student, undergraduate, I've always said anybody can take the course. I've given parts of this course to John Deere in Davenport, Iowa, to their engineers. And they've had some of their welding technicians come and take the course. These are guys who probably graduated from high school, maybe. And could they take the course? Yeah, because I'm not here to confuse you. Okay, a lot of professors want to show you how smart they are and how dumb you are. Okay, my goal is to prove to you that you actually already know the answer to things. Just no one's ever told you how to put the answer together. Okay, but you've actually learned as MIT students, you took your freshman physics and chemistry. And you know, there was this book a few years ago, Everything I Needed to Know I Learned in Kindergarten. Okay, everything you need to know for this course you learned as a freshman. Okay, sort of. Now, I might go into some other topics that you don't know about, but stop me. I love questions. Okay, students will tell you, if they've taken the course, I'd much rather answer your question and go off on a half-hour digression on whatever you asked than to give this lecture, which I've been given for how many years? Okay, I've heard it before. So it's not that interesting to me. The requirements, so you got to do a presentation. If you got acrophobia, what's acrophobia? It's the #1 fear.
Fear of heights.
No, maybe actually maybe.
Acrophobia is fear of heights.
Is fear of heights? Maybe I think is it agoraphobia? Anyway, fear of public speaking. Okay, is the #1 fear. I probably got it wrong. Anyway. In any case, some people are deathly afraid of public speaking. If so, you can come and you can talk to me, but frankly, what's the big problem? I'm not going to make all of you sit through all the lectures, okay, or your presentations. I will come up with a schedule later. We'll probably be doing these somewhere between Halloween and Thanksgiving. You're going to be done with this course if you watch these other videos. You'll be done by Thanksgiving. And so when it gets to be December and all the other courses are piling up on you, you don't have to worry about this one, okay? I remember what it's like to be a student around here and how the professors procrastinate. Okay, one of the problems around here is I say that 95% of all the pressure at MIT is self-inflicted. Whether you're a student or a faculty member, it's self-inflicted because you procrastinate. So we're not going to procrastinate. We're going to meet every day. And we're going to be done with the lectures, the live lectures, before the end of October. If you're smart, and you're supposed to be smart because you got admitted to MIT, you will watch these other videos. One student said they watched them while they fixed dinner. Okay? So I don't care when you watch them. you're not going to be quizzed on it. Just, think of it as watching a video game or something, or, Indiana Jones. Maybe not as exciting as Indiana Jones, but anyway. Okay. I don't have to tell you about collusion because there's no quizzes. Okay. Cooperation. You're welcome to cooperate in any way you want. When I taught thermodynamics, I used to say, and I don't like memorizing. I hate memorizing. I used to tell the students for a quiz, it was an open book quiz, and they could also bring in a one page sheet of paper, and they could write on all 6 sides of the piece of paper whatever they wanted. And I used to tell them, even though it's open book, if you have to look at the book, you're not going to have time to finish a 1-hour exam. Okay? If you really know what you're doing, you don't need to do that. If you figure out, when I taught thermo, there was only, actually handed out a 1-page sheet of all the equations you needed. Okay? Because you can derive all the others. Okay? If you know the fundamentals. So we're going to try to talk about the fundamental principles of things. Any questions? If you don't want to do a presentation, you can do a term paper, or we'll figure out something else. I will probably, if some of you are willing to come in at like 8:30, I'll probably try to get when we're doing presentations. I'm probably going to ask you to attend 8 or 9 presentations, okay? Your own plus 7 or 8, okay? You don't have to attend all of them. I'm the only person who has to attend all of them, okay? And so we can probably get the presentations done in a week and a half with this many students. If I can do 3 or 4 a day, if some people are willing to come in a little bit early, we can do some of them at 8:30 and get 4 done in a day. I've done that in the past. And anyway, if we need to, we can get your breakfast. So I actually did write something about some of my philosophy about what makes MIT MIT. It's in something I wrote for the MIT faculty newsletter. There's another handout. I actually would encourage you to read this, particularly, well, whether you're an MIT undergraduate or a graduate student now who didn't attend MIT. When I teach the Navy students during the summer, I actually hand this out because I'm trying to introduce them to what MIT's like. MIT's unique among many of the schools in the country. I think it's not completely unique. Caltech's the other one that only admits 1 class of students. MIT only admits 1 class of students. What's that? Scholars. Some of you have heard this talk before, right? Those of you that are internship students. And you've gotten this paper before, so far as that goes. Other schools like Harvard admit 3 classes of students: scholars, athletes, and legacy students, which are sons and daughters of wealthy alums. Okay? We don't have that here. And because of that, we can throw all of you into freshman requirements. You get no electives in freshman year, basically. And we homogenize the class. Okay? You're all just as dumb as all the rest. Okay? And you were top of your class, now you're average. Okay? But in fact, I wrote this, in 2004 or something. And a number of, gave it to a number of alums. And they say, oh yeah, that's what MIT is all about. Well, I went there too. I know what it was about, and that's why I wrote it. To give you some idea of what makes MIT unique. So I would encourage you to read it. It has nothing to do with structural materials. There is another paper that I'm going to give you, why the World Trade Center collapsed. And a lot of you have seen this paper before. I give these out to a lot of students. This is a paper, I've written in my career a couple of 100 peer-reviewed publications and stuff, and that was, I remember the first day I met as an assistant professor, I met with Walter Owen, the department head, and he said, no matter what anyone tells you, it really is publish or perish. Okay? That was the only advice he gave me in the next 6 years while I was a young assistant professor. But you have to publish. So what happened here was about 2 or 3 weeks after the World Trade Center collapse, an editor of a metallurgical journal actually asked Professor Clark, Joel Clark, if he would write an article. And Joel says, no, why don't you get Tom Eager to write an article? So he called me and he said, will you write an article on the World Trade Center? I said, yeah, I'm so sick of hearing things in the newspapers that are absolutely wrong, such as the steel melted, okay, that I decided to write a paper. And I wrote the paper, and I wrote it with the idea that I was writing this for a good high school science student that knew a little physics and a little chemistry, but at a high school level. It took me 3 hours to write this paper, total. Okay, Chris Musso videotaped some professors in civil engineering giving a little lecture in early October about the structure of the World Trade Center. So he did a little research for me, and that's why he's the second author. Took me 3 hours. I spent less time writing this paper than any of those other several hundred papers. I have had more comments on this paper than all my other papers combined. So all this little minutia research that I've been doing all my career, no one cares about. But they do care about the World Trade Center, and they want to know something about it. And I wrote it in a way that hopefully lay people can understand. Just like those technicians at John Deere, okay? They could get some things out of things if I talk to them, not above them, okay? Actually, I got another story about when I was doing those video courses for General Motors in the early 80s, or early 90s. I got a phone call. I remember I was department head at the time, and I got a phone call from a couple of engineers at one of the GM assembly plants in Ohio. And this course was open to any GM engineers, but it wasn't supposedly open for the hourly laborers, okay? And it turns out there was a shop steward in Ohio, shop steward in the union, right? And he wanted to take the course. And he had a college degree in philosophy. And so it was like a $2,000 tuition at MIT to take the course and get credit for it. And the manager of the plant, now this is probably $1 billion plant, right, at General Motors, right? Everything's $1 billion at General Motors. And he didn't want to pay the tuition. He said, well, you're a philosophy major, how could you take an MIT graduate course? And the engineers who worked with this shop steward thought, well, this guy really is curious, and they wanted him to be able to take it and convince the plant manager. So they called me up and they said, well, what do you think? Do you think he can take it? And I said, well, you know, you tell that plant manager that if he takes this course, he lets this guy take the course, and he doesn't save General Motors at least the cost of the tuition, I will personally pay the tuition. So we go and start taking the course, and I was talking about adhesive bonding, and I mentioned that in adhesive bonding, cleanliness is next to godliness. You've heard that phrase, right? Okay, not about adhesive bonding before, maybe, but it is. You know, if you got a greasy surface, you try to stick Scotch tape to it. It doesn't work, right? Because you got surface contamination, right? But so he calls me up about a week after the adhesive bonding lecture. He says, you know, we're in the plant, we're gluing down the carpeting on the cars, okay, on the inside of the cars. And we've had consultants coming in here, and it wrinkles. The adhesives are not working. And in adhesive bonding, you said cleanliness is next to godliness. Do you think it has anything to do with this water jet cutter robot we have right next to it about 10 feet away that's cutting the carpeting to the right shape and is creating a mist of, you know, particles and water everywhere? I said, yeah, probably. So he got some screens and, you know, things and convinced them to, you know, have some ventilation to pull all that stuff aside, and all of a sudden the carpeting started staying down because the adhesive worked. And they saved over $100,000 for General Motors that year. Okay, and all these other consultants had come in, they couldn't figure it out. But this guy with a philosophy degree, if you understand the basic principles, and the basic principle on adhesive bonding is cleanliness is next to godliness, okay? Is this that hard? Do you need to take notes about that? Okay, so anyway, so that gives you an idea of what to do, and I didn't have to pay the tuition. Okay, I guess the plant manager ate it or something. Anyway. So, in this course, anybody have any questions? I'm now going to start talking about the course. We're halfway through the hour. So this is from the Christian Science Monitor of 25 years ago, and it says, at the Graduate School of Business, and how I know you all want to make money, but today we're going to discuss making things, actual things. This is a production management course. And the guy down here says, things, I don't want to make things. I want to make money. Listen, we could sue the business school. We could make some money that way. Okay? And that's kind of gives you part of my opinion of business schools, having been through the Sloan School. I'm actually considered an alum of the Sloan School. I took their senior executives program in 1988. But we're going to talk about structural materials here. And today, I'm going to talk about externalities. Anybody know what externalities are? Anybody had an economics course? Yeah, okay. Right. Externalities is a word used by economists. None of you have ever had an economics course? Okay, so did you ever hear externalities? Oh, well, okay, see? Okay, okay, a cultured man, okay? Anyway, economists like to talk about externalities. And the externalities that they're interested in are things that like political, social, economic, well, of course economists are interested in economics, cultural, environmental, and it turns out a lot of the engineering you've got to do today is going to be influenced very heavily by these other things. And there's an article here that I'll pass out. See, you have some homework reading if you want to do it, but these are actually, hopefully they're going to be fun things to read. This is called Socio-Engineering and Augustine's second law thereof. Norm Augustine was, or is an engineer. He's probably close to 80 now. He's an engineer, graduate of Princeton University, became the CEO of Lockheed Martin Corporation, pretty good sized corporation, a member of the MIT Corporation. We don't have a lot of non-alums on the MIT Corporation, but Norm Augustine, I mean, he was asked to be the president's science advisor, turned it down, okay? He wrote a wonderful book. That's how I first got to know him, when he was just a kind of a middle-level engineering, called Augustine's Laws, and you'll die laughing when you see some of these things, okay, that the military did. But anyway, he is kind of poking fun at things. But he is a national spokesman for engineering. And this is an address he gave it's published in the fall of 1994. It was actually part of a commencement address in October of 1993 at Colorado State, University of Colorado, at some engineering centennial convocation or something. And it talks about socio-engineering. And he talks about the ages of engineering and how we've gone through a historical ages. And by 1993, he says, now if I want to go out and do some engineering, I have to worry about all kinds of other consequences I never had to worry about before. Okay, so what do I mean by that? We're going to talk about some of these things. I'm going to give you a sort of homework. You don't have to turn it in assignment. But, so one time, about this same time, in the early 90s, I was asked to go look at an explosion that occurred and killed a woman welder, threw her across the river when this tank blew up that she was welding on, at a place, an oil refinery in Oil City, Pennsylvania. Anybody from Pennsylvania? Western Pennsylvania? Oil City, what's it near? Nothing, right? Yeah, that's right, okay. But what's north of it? Titusville. You ever heard of Titusville? What happened at Titusville in the 1850s? You don't know, okay. Anybody else know? Edwin Drake drilled for oil. First oil well in the world in Titusville. Pennzoil. Ever heard of Pennsylvania Oil Company? Pennzoil? So this was a Pennzoil refinery just down the river from Titusville where they first discovered oil. This refinery had been built about 1900, okay? And so I go there and it was an old riveted steel tank from the 1920s that had blown up. And it was corroded around the bottom. And the first day I was there, we're at the tank farm, and the tank farm's got all the gravel between the tanks. And it turns out if you dug down about 1 foot, you'd strike oil. They had been spilling oil around these tanks for 90 years. And, you know, you go down 1 foot through the rock, and there's oil, okay? Sort of an environmental mess. But it was a small refinery, okay? And I thought, that night, I had to be there for 2 days. And that night I thought, how could Pennzoil great big multi-billion-dollar corporation. How can they afford to run a little refinery like this? And the next day I realized they couldn't afford not to run it. Anybody know why? It's an externality problem. Yeah.
The cost of the cleanup.
Cost of the cleanup, exactly. If they shut it down and moved out, they were responsible for hundreds of millions of dollars of cleaning up all that oil they've been spilling for the last 90 years. If they kept on running it, they could leave it polluted. Okay? And so they couldn't afford to shut it down. Now, since then, it has been shut down. I have a graduate student who comes from that area of Pennsylvania, and he's told me that they have shut it down. But they had to go, because of the Environmental Protection Act, it becomes a hazardous waste site, and Pennzoil is responsible, sort of an extra tax on having polluted in the past. But the rules for pollution have changed over the years. Okay? Do you know how they used to get the oil from Titusville down to Oil City to the refinery? They just floated it on the river. Just pour it out on the river, they have a weir at the other end, skim it off the water. Not a lot of fish back then. Okay? Now, if you did that today, what would happen? Okay? Bang, you're going to jail. Okay? So the rules have changed. And in fact, a lot of you have learned, and most of my colleagues on the faculty in the 1980s and 1990s looked at the steel industry and said, this is a dying industry. And I can't even keep track. Some guy asked me to help him on a problem for a steel company, and he named the steel company. I never even heard of the steel company. I used to work in the steel industry. Everybody's buying them out. Okay, that used to be the biggest steel company in the world was a company called U.S. Steel. Okay, Andrew Carnegie. You ever heard of Andrew Carnegie? In his day, he was richer than Bill Gates was, or whoever's the richest person in the world today. Is it Carlos Slim? Okay, but anyway, but he was much richer in constant dollars, and he made it all on steel. And you're going to keep hearing the word steel for about the next 4 or 5 lectures, and you're going to get sick of my opinion of steel, okay? That it's actually an important material. Because everybody in the 1980s was saying steel is a dead industry. Was it? What's happened to steel today? Well, the Chinese are buying lots of steel, started buying lots of steel about 10 years ago, and steel has become a very important material. So, in the early 1990s, I wrote a paper. No one else would publish it, so I published it in the Welding Journal, called The Future of Metals, okay? Because at that time, I'd spent a year over in Tokyo, Japan on my sabbatical in the mid-80s, and they had something called ceramics fever. Ceramics was the material of the future. They had a ceramics conference in Shinjuku in Tokyo, which is the world's largest subway stop, okay? About 2 million people a day go through there. My 10-year-old son got lost in Shinjuku once, okay? Fortunately, he was with some other people. I said, we'll go to the next subway, couple of subway stops down, I'll come pick you up. Anyway, but Shinjuku, they had a conference, and they had 2 million people go to this ceramics conference. Can you imagine? I'm not talking about ashtrays and stuff. I'm talking about fine ceramics like, you know, scissors or knives or, you know, substrates for semiconductors or things like that. The Japanese just enamored with fine ceramics. And people in the United States were, oh, metals are going to die. Ceramics are a much better material. Okay, well, I'm going to teach you about selection of materials. And at the time, I actually went down, when I got back in the mid-80s, I was so sick of hearing this stuff about how wonderful ceramics are. I went down to the National Institute of Standards and Technology in Gaithersburg, and I had to give a talk. And I got up in their big auditorium, and I said, well, let me tell you about ceramics, fine ceramics, and whether they really are the material of the future. Because people said, oh, we're going to have, this is 1985 or 86, they're saying, we're going to have engines, automobile engines. They can run at higher temperatures. Ceramics will take much higher temperatures than metals. And they don't corrode, okay? And I said, look, the only 2 high-volume materials made out of ceramics are Portland cement and toilet bowls, okay? and I'd throw in the kitchen sink, but you got to line it with cast iron to give it fracture toughness. Okay? Well, I didn't get a lot of friends for saying that in the ceramics business. Okay? But in fact, it was true. And so I wrote this article called The Future of Metals, and I said metals are important. Well, the very first plot here, if you look at metals, this is something most of you probably didn't know, but 95 pounds out of every 100 pounds of metal made in the world is steel. How about that? Did you know that? Aluminum is a big 1.75% of all the metals in the world. Okay? So why do we select steel all the time? Well, we're going to talk about that. I'm not going to tell you everything in the first lecture. I got to save some of the things. But I do have something I put together last fall, which kind of is a follow-on to that. And this is the world tonnage for structural materials. Some structural materials, not all structural materials. There's steel, 1.5 billion tons a year. There's aluminum, 45 million tons a year. Copper, 15 million tons a year. Okay? Keep on going down. I got some odd things on here like scandium. Then we only produce 2,000 tons a year of scandium. When we get to aluminum, I'm going to tell you why we use where we use some of our scandium. Anybody know where we use some of our scandium? Some of you. I must have given this lecture to some of you undergraduates. Anyway, we'll talk about that. Okay, lead. We still make 8 million tons a year of lead. Okay, but the biggest use of structural material is stone. And this is a Tom Eager estimate. We probably use about 6 billion tons of stone a year. Okay, crushed stone. Okay, how come nobody in this department is studying stone? Okay, we use more of that material than anything else. There's a guy at Harvard, one of the top scientists, the father of fracture mechanics. He's not the father of fracture mechanics. Jim Rice, probably a little bit older than me, maybe 5 or 10 years older than me. But in the area of fracture mechanics, Jim Rice is here, and the next best person in the world is down here. Jim Rice came up with, the J integral as part of his doctoral thesis at Lehigh University. He was a student at Lehigh, and ever since, all the fracking that's going on, all the oil and stuff, Jim Rice, 20 years ago, was teaching people about fracturing rock. Okay? And a lot of the fracking that's going on is based on his knowledge of fracture mechanics and studying rock. The next largest, which is 1.5 times the volume of steel, Portland cement. I told you the largest volume of ceramic in the world is Portland cement. And how long have we been using Portland cement? The Romans used Portland cement. And the Roman cement is some of the best cement in the world. 2,000 years later, it's still there. The aqueducts, the Appian Way, made out of cement. Turns out volcanic ash certainly has certain advantages for making cement, but I don't understand all the reasons. And plastics, plastics. After ceramics in the 1980s, plastics. That's The Graduate, right? Anybody watch the movie The Graduate? Don't you remember the thing? The hot tip was plastics. Okay, that's the future, right? Well, plastics have only been around for about 50, 60 years, and we use in all the plastics about 300 million tons a year. Okay, and so this Future Metals paper, I kind of put this stuff together, and I pointed out that the growth in the steel industry over the next 10 years, and this is somewhat dated, it's a 25-year-old paper, but it doesn't matter. What's wrong with an old paper? The growth in the steel industry at 1 or 2% a year was going to be a larger growth rate in dollar terms than all the other advanced materials people were talking about. Semiconductors, how large is the semiconductor industry? In dollar volume. I mean, let's not compare tons. I mean, semiconductors are not structural materials. It'd be apples and oranges, right, to compare on a tonnage basis. But on a dollar basis, the worldwide semiconductor business, to make chips, 250 billion. The steel industry's $1 trillion. Okay? So, the last department head before Professor Shu was a guy that wasn't a great friend. He'd been my associate department head when I was department head, but he used to say metallurgy was dead, okay? And he said he was a plastics person, and he thought plastics was where the future is. So I published this paper, and I used to give these talks, and my colleagues would say, on the faculty, say, really? Steel's that big? Okay. Well, the aluminum industry is pretty big too, okay? But it shrinks compared to the steel industry. We're going to talk about why, okay? And why steel has certain advantages over cement and stone. You can probably figure some of those out for yourself. But we're going to try to quantify some of these things. Okay. So what about the externalities, okay, of these things? Other externality things. So the externalities can be, might as well write them down. If you want to take notes, you can take notes of this. But political, political factors, economic, social, cultural, environmental. These are all externalities. Cultural, did I put down cultural? Military, well, okay. I'll put down military this year. I have some theories about military technology. Regulatory. Okay, so these are some of the externalities. There can be other externalities. Anybody got another externality? Some other factor that influences how we engineer materials or why we engineer materials. I told you about the Pennzoil plant and why they kept it open, even though it made no economic sense. It made a lot of environmental sense economically, okay? But because of some regulation, okay, so far as that goes. Anybody have an idea of any other externality of something? Anybody? Well, so let me know if you can think of something. Yeah.
What do you call the externality for
The
the future's going to have to worry about?
future is going to have to worry about what?
Yeah, nobody in today's political landscape has to worry about it.
Oh, that's called copping out. I don't know. I mean, it is an externality of people don't want to face the music. Is basically what you're saying, right? But that shows up in a lot of these. I mean, that's sort of another dimension cutting across these types of externalities in the sense of nobody wants to pay the price today, okay, of what's going to happen in the future. And you can say, well, that's in the environmental thing. That's what happened at the Pennzoil plant. You know, they wanted to work things as cheaply as possible. Okay, I learned about doing things as cheaply as possible. MIT had the World Economic Forum here back in the early 90s, and I was running the session on the environment. And I had the head of Tata Steel in India, and I had Danilov or something. Anyway, his first name and his last name were almost the same, which is not uncommon in some parts of the Soviet Union. And he was the minister for the environment. And some other people, they were on this little panel, and I was the chair of the panel. And someone says, well, you know, this is the early 1990s. They said, you know, you've got oil pipelines in Siberia. They're just gushing out oil in leaks. Why don't you fix them? And he said, well, you know, in 1985, when we first had glasnost, and people in the Soviet Union became very interested in the environment. But today, 6 or 7 years later, they're really just interested in eating. Okay? And you find that people who have a fairly high standard of living will be very interested in things like the environment because they can afford to. Does anybody know what Maslow's hierarchy of needs is? So a lot of people are. Maslow's hierarchy of needs. First, you got to take care of your food, shelter, and clothing before you can start worrying about all these nicer things. You go Google it, and you'll find a little triangle for Maslow's hierarchy of needs. And at the bottom is basically food, shelter, and clothing. If you don't have those needs met, you don't care about a lot more. And someone asked the Irani, who was I think it's Jamshed Irani, was the chairman of Tata Steel. He said, why do you make steel in such an environmentally unfriendly manner in India? And his answer was, he says, well, India has some of the cheapest iron ore reserves in the world. $5 a ton for the iron ore, whereas you might be paying a couple $100 a ton, $100 or a couple $100 a ton somewhere else, Brazil or something. We've got some of the cheapest iron ore reserves in the world. The United States used to have them, they called it Mesabi Range up in Minnesota. But World War II, we basically dug it all out. So we had iron ore in the Mesabi Range. You could just take it as crushed stone and put it in the blast furnace to make steel. You didn't have to do any cleaning or processing, get rid of all excess materials. It was just perfect grade ore. Anyway, so they asked Irani, why do you make steel? So, why don't you make it in a more environmentally friendly manner? He says, well, India has some of the cheapest iron ore in the world, and India needs foreign currency. And we are going to make steel to generate foreign currency for our country. And we don't want to make it in an environmentally unfriendly manner, but we don't have the technology, and we don't have the money to pay you for the technology. If you will give us the technology to make it clean, make it in a more clean way, we will do it. They don't want to make, why would they want to live in a place that's like Pittsburgh was in 100 years ago? Okay? When I was your age, well, not quite, but if you went back 10 years earlier than that, when you were, when I was in elementary school, people in Pittsburgh couldn't wear a white shirt for a whole day if they went outside. The air was so bad in Pittsburgh. This is why in 1972 they came up with the Environmental Protection Act. A lot of it was because of the air in Pittsburgh. Don't think about Los Angeles and smog. It was the steel mills in Pittsburgh. Okay, dirty as could be. Okay, so that's you. Anybody think of an externality or something? Anybody know what these are? These are magnets, right? Different types of magnets. These are ceramic magnets. This is a cow magnet. Anybody know what a cow magnet is used for? Yeah. Well, actually, you want him to digest the barbed wire, or her. Actually, her. You basically feed it to him like a pill. It's a big pill to swallow, but not for a cow. And it's stainless steel magnet, actually. Okay, and it doesn't dissolve in the cows in the, hydrochloric acid that we all have in our stomachs because it's stainless steel. And if the cow has eaten some barbed wire, some old rusty barbed wire, it will attract the barbed wire, and the steel over the next couple of days will stay in the stomach and will dissolve. A little extra iron in the diet, it's not bad for any of us, right? It's not toxic. But if the cow tries to pass it through, that barbed wire can do havoc on the rest of their body. So they feed cows magnets. Okay, this is a cow magnet. Very cheap way to get a decent magnet. But anyway, there are also other magnets. This is a neodymium iron boron magnet. Okay, invented by General Motors research. It's much stronger. The strength of a magnet in energy terms goes as the magnetic field squared. So if you go from the ceramic magnets, what might be 10 kilogauss, 10,000 gauss, to a ceramic, or not a ceramic magnet. Actually, this magnet, an alnico magnet, might be 7,000 gauss. 10,000 gauss for a ceramic magnet, 40,000 gauss. So start squaring 40 compared to 10 or 70. Okay, lots more energy, and it turns out that when I was your age, the starter motor on a car weighed about 15 or 20 pounds, almost all copper, and it had alnico magnets in it, but it was about almost the size of a football. Okay. Today, the starter motor is not much bigger than your fist because it's got much stronger magnets in it, permanent magnets. Takes less copper, save 10 pounds of weight on the automobile. So what's the externality on neodymium magnets? It's actually 4 or 5 years old now, huh? Well, wind turbines use them, yes. Okay, wind turbines use the magnets. But the externality was a political one. Almost all the rare earths come from China now. Anybody know what happened 5, 6, 7 years ago? Because the Chinese believe they own these islands between China and Japan. They decided to cut off the supply of rare earths to Japan. They just said, we're not going to sell them to you anymore, overnight. And all of a sudden, Hitachi and a bunch of Japanese companies that make rare earth magnets were about to, you know, their billion-dollar business was about to go under, because the Chinese decided politically this is an externality in the rare earth magnet business. Okay. There are a lot of other externalities, and maybe on Monday I'll talk about a couple of others. I get telling stories, and I always go a little bit slower, but that's why it takes 12 lectures to give you 2 lectures worth of content. So you can, your homework is to, not that you have to turn it in because I don't want to grade it, is to think about, can you think of some externalities of where we're engineering something differently because of some factor, okay? I'll give you a cultural, another political one. Blood diamonds. Anybody know what blood diamonds are? That's a few years ago, okay? They're having a civil war in Angola, and some of the separatists were basically taking over the diamond mines, okay? I go back 40 years ago, Rhodesian chrome in Africa. Chrome ore, Rhodesian chrome ore is the best in the world. Okay? We can get chromium from a lot of other sources, but none of it's as good and as economical as Rhodesian chrome. And they were trying to, same type of thing we're trying to do in the Ukraine right now is politically, you know, get them to the Soviets, former Soviets, to do what they should be doing, or in our opinion. Well, they tried to do the same thing and have an embargo on Rhodesian chrome, except you could always tell it was Rhodesian chrome. They launder it through some other country, but no one else had that kind of chrome ore. Okay, so they knew they were really selling Rhodesian chrome. But so on Monday, let's see if you can come up with some externality stories, okay, of some factor. That's your homework, and you can read these other things, and I'll see you then. Thanks.